Okay, so this is already lecture 3. Okay, today, once again, we are working with Laplacian operator. Once again, we are working with Laplacian operator. So we have already discussed about the three-dimensional form of Laplacian operator and its simplification in one-dimensional structure. So this Laplacian operator was the key operator of our previous eigenvalue problem. That is, eigenproblem and that makes one a big category in the computational microelectronics. However, this is not the only problem of our interest. There is another type which should be considered in this course. That is differential equation. Especially, we wanted to solve the differential equation with appropriate boundary conditions. Where can you find the boundary condition for your study in this course? For example, we introduce a certain concept called device. This device is actually some combination of certain materials. So here we have wafer, usually made of silicon wafer. Its thickness is around 600 micrometer, and we make some spatial inhomogeneity on or near the top surface of our silicon, just in a few micrometer scale. We make tiny structures to realize a certain function. So, although in its vertical size, this part is really short compared with this long entire silicon wafer. However, electrical sense, actually this one plays an important role. So we call this small part of silicon wafer as a device when that is functioning for our functioning according to our intention. If we apply certain voltages to this region and apply another voltage to this region, then that can introduce certain electrical reactions like current flowing through into this line. Then we will call this kind of operation as a device operation, and this structure is called device. Let's come back. Device is actually quite small. So small means that it is really in micrometer scale or even smaller, like nanometer scale. Then if we have a certain view like this is just micrometer scale, and this is also certain micrometer scale. And although I have drawn it as two-dimensional structure, we can easily understand there is a third dimension like also this scale at most micrometer scale. You know, in reality, this size micrometers, this is a little bit larger than these days. Actually, in these days, this one becomes just 0.1 micrometer or even smaller. Also, this one becomes even smaller than micrometer scale, and also this is even smaller than micrometer scale. But anyway, that doesn't matter. So anyhow, this box is already quite small. This small box, this small box, we have introduced, for example, here certain, let me erase it, certain area where its doping density is especially higher than the other part. Also, we introduce another reason where the doping density is especially higher than other part. Yes, we have made certain specific reasons where doping density is intentionally higher than other parts. After that, we apply certain voltages to directly in this part and directly in this part. So therefore, that here, although we have a box in this problem, actually this boundary and this boundary have completely different characteristics. You know that if we are interested with electrostatic potential, what is electrostatic potential? We will discuss it later. But if we consider electrostatic potential at these 2 points, we can say the electrostatic potential at this point is governed by the applied voltage at this highly doped region. And how about this? At this point, we have no idea. There is no predefined condition to determine this value. When we solve certain differential equation for semiconductor devices, then depending on the device, depending on its shape, spatial distribution, we can introduce various boundary conditions. So we cannot predict whether this part will be certain boundary or not. Let's say that always we are talking about just a two-dimensional box, and there is the same size two-dimensional box, and you wanted to analyze these two different devices, but happen to be this one has terminal here and there. This is your first case. And say you have introduced contact here and another contact here, and even the third one is placed in this way. Then what will happen? Can you expect that the property of your device is the same for this one and that one? Obviously, you have to say that although this internal box has the same property depending on the position of your contact, the operation of your device 1 and device 2 will be differed. Okay, so let's come back. Boundary condition, treatment of boundary condition is quite important. And this is, let's come back the main story. In summary, 1, there is eigenvalue, eigenvector problem, eigenvalue equation. Then second one is differential equation. We have to be able to solve this first category and second category. And in a previous lecture, lecture 2, we have studied how can we solve eigenvalue problem. So today's lecture, lecture 3, we will study the solution of differential equation. There can be so many differential equations in principle, but usually we are interested in this course. We are interested just limited number of differential equations. Let me allow just name important ones. The most important one and most frequently used one, there are two actually. The first one is the Poisson equation. And the second one is electron or hole continuity equation. These two equations are the most important equations used in the computational microelectronics, and they have similar shape, so we can start from a little bit more simpler one, the Poisson equation. But even the Poisson equation is not easy enough to start from the scratch, so let me allow a little bit even simpler one like Laplace equation in today's lecture, lecture 3. This will be just a starting point for our study on differential equation, and differential equation will be later Poisson equation and continuity equation. Okay, so then let's go to the next part. Still, we will work on the simple 1D structure whose range is given by larger than 0 and smaller than a. And now our boundary condition should be supplied. Here, if we have one-dimensional structure, then there are only two boundary points, x equal to 0 and x equal to a. So in this 1D problem, we have to specify what and what. This is enough for our boundary condition. Then how about the two-dimensional case? If we are working with a two-dimensional case, then now we have this box-like structure. Then, of course, one way is to set the values around all these peripheral area or peripheral region of this box. You can specify value at here, 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 here. At every discretized point on the surface, you can specify the value. That can be a case. However, let's come back to our previous discussion about device, semiconductor device. Then, usually, we have here and there certain structure called contact, and this is semiconductor. So this is a semiconductor, and this is actually metal, and also we have metal. Therefore, if we are working on semiconductor region only, then certainly we can say this part, and this part has certain properties related with metal. Also here, the property of our solution variable will be governed by this metal. That's quite easy. But point is, how about the point located here and here, which is not directly attached to the metal? Then metal cannot make any influence on it directly. Then in this case, we cannot specify the value of unknown variable on this point. So different rule is required for this non-contacted point. Okay. Therefore, we have to introduce two different types of boundary conditions. For example, this circle point. In this case, metal decides the unknown variable. So if we say the unknown variable is written as, for example, phi, then we can say at these circled points, phi equal to certain values, 1, 2, or 1.5, something like that. This is possible. However, these squared positions, in this case, metal does not play any role in its characterization. So we have to describe the boundary condition at these non-contacted point, and it really depends on the problem. However, let me just give you the practical answer to this question. In principle, what is the boundary condition for this squared point which is not attached to the contact? In principle, there is no restriction about boundary condition, or actually we have to find out the most appropriate one by ourselves. However, if we restrict ourselves to just Poisson equation or continuity equation, two most widely used equations in our course, then in these specific cases, the flux related with the problem becomes zero. For example, if we are considering so-called Poisson equation in this computational microelectronics, then the flux becomes just displacement which is proportional to electric field. In this case, we will say for Poisson equation, displacement vector d and n. So displacement vector in the direction of out normal direction becomes zero. Also, in the case of electron continuity, the related flux becomes the flux of electron or flux of hole. In this case, we will say flux of electron aligned to abnormal direction becomes zero. So we will use this kind of boundary conditions for our equations. So this is not quite much general discussion. Instead, that is really specific to our most interested equations like Poisson equation and continuity equation. So in summary, I'll give you a practical tip in our lecture. I can summarize in this way. A point in the contact, then we will assign a value. Therefore, this is so-called Dirichlet boundary condition. And a point without the contact, in this case, we will just apply homogeneous Neumann boundary condition. So in the case of one-dimensional structure or two-dimensional structure, three-dimensional structure, we will work with this simple principle. If you have contact decides the value. If you don't have contact, then no flux is allowed crossing that domain boundary. That was just a general comment on boundary condition, which is valid for general dimension problem. And let's come back once again to our simple 1D problem, 1D Laplace equation. Since our equation is just a second order derivative of our function, function vanishes. So at most it can have just a linear term or a constant term. This is linear and this is constant. However, both of them vanishes when we take the second order derivative. So this is the possible form of our solution. And why don't you say we introduce two undefined coefficients like C1 and C0. Of course, they are just constants and coefficients, so that doesn't depend on x. Then, when we apply the boundary conditions, we can decide the value of C1 and C0. For example, if we introduce x equal to 0, in this case, according to our boundary condition, it should be 0. And when we consider the testing form of C1x plus C0, then when we insert x equal 0, then it becomes just C0. Oh, therefore, C0 is also 0. Then let me consider phi at A. In this case, it should be 1 according to our boundary condition. Then it is 1, and in the test form, we will have C1A plus C0. Of course, C0 is 0 in this case. C1 equal to 1 over A. So by collecting this information, then eventually we have phi is given by x over A. So phi becomes x over A. Why don't you just draw it? If we draw this one, then here x and 0 A, and now we have 0 and 1, 0, 1, and in between this is just a straight line. So this solution itself is quite simple. However, please concentrate on the general description. We can easily make a much difficult or much complicated equation by adding some terms in the Laplace equation. So Laplace equation itself is quite a simple equation, but please try to remember the discussions, general description about differential equations. Okay, then where can you find such kind of situation? Let's say that now here, there, you have introduced a dielectric material and make a parallel capacitor, a parallel plate capacitor, and this part is just grounded, and this part is connected to a voltage source whose magnitude is just 1 volt. And my question is, what is the voltage at this position or that position or another position? Such a question can be answered by this Laplace equation. If you are at the middle point between this grounded contact and 1 volt biased contact, you will have just 0.5 volt. And if you are close to the ground contact, then your voltage will be reduced. And if you go to or approach to 1 volt biased contact, then your voltage will increase. That is easily answered by this simple Laplace equation. Solution procedure is quite easy, and it has been already discussed in our previous lecture. So we will assume there are uniformly distributed positions here. So positions starting from x1, it is 0, and xn, which is given a, and they are uniformly distributed. So for example, x2 becomes just delta x, x3 is 2 times delta x, and if you have xi, then it is I minus 1 times delta x. Yes, so that is our assumption. Then our solution function phi now can be expressed in a vector form, like the values at sampled values at x1, sampled values to x2, and sampled values at xn minus 1, and finally at the final point xn. And as I told you before, in this course, instead of this long expression, sometimes I will make a short-handed form like a phi 1, phi 2, and phi n minus 1, phi n, when everything is clear, not introducing any confusion. So just considering a limited information for sampled points, our grid points, we are satisfied. We will believe only finite information about the solution function phi is enough to reconstruct the original solution. That is our assumption. We have discussed it in a previous lecture. So we will keep this solution vector. Solution vector. Yeah. For example, if we have 100 points, then it becomes just 100 by 1 column vector. Okay, if we have introduced 500, then that will be 500 by 1 column vector. So we wanted to find out the value of these quantities. Yes. Then, since we have differential equation, second order differential equation, yes, so we were quite successful to express it in a vector form, phi 1, phi 2, up to phi n minus 1, phi n. So this right hand side 0 is also casted into a vector form. Here vector means that this one line, another line, or one row, another row, or different row, they are corresponding to the Laplace equation evaluated at that point. So let me repeat again. When x equal to xi, then we can evaluate the Laplace equation at certain position, x equal to xi. Then, as you know, that becomes just this number, and I plus 1 minus 2 times phi I plus phi I minus 1 becomes 0. And this relation, which is the Laplace equation evaluated at certain position x equal to xi, is assigned to this i's law of our system. And you know that we can easily recognize it as just a leading coefficient, and just a row vector where all zero component everywhere except for -2 for the ith position and 1, 1 for I minus 1th position and I plus 1th position. So now this one, of course, it is not enough. Of course, we have to have phi 1, phi n. Then this row vector and column vector multiplication gives you just a scalar, and that scalar is given by 0 only due to the Laplace equation. So when you consider it, then you can feel this law like this: 0, 0, and 2, -2, 1, 1, and here 0. Also, when you change your evaluation position xi, but if you say I plus 1, you will follow exactly the same thing, only with one shifted index. So if we assign the I plus 1's law, then that will give you the same pattern, however, one shifted to the right. So 1, -2, 1. And how about this? If you are going to 2 times, then you will have 2 times shifted, so 1, -2, 1. That will give you the full information about your system. You can evaluate Laplace equation for many different positions, and every realization of or every evaluation of a Laplace equation at different point will give you a different equation. So they are just collected in different law. Okay. Of course, since this second order derivative can be evaluated for what? You can apply your evaluation position. For example, you can evaluate it x2. You can do it. x3, you can evaluate it. And xn minus 1. Also, you can evaluate this Laplace equation. But how about x equal to x1 or x equal to xn? In these two cases, you will have a practical problem or practical difficulties. I wanted to evaluate it for x1. Then you will find that this is corresponding to phi 2 minus 2 times phi 1 plus phi 0. Oh, but what is phi 0? Is there anything phi 0? So phi 0, this is phi f defined x equal to x naught. But you know that there is no point like x naught. So this is not properly defined. Also, when you consider this xn case, then you will have something like coefficient and phi n plus 1 minus 2 times phi n plus phi n minus 1. You know this, and that can be really accessible. However, we have no idea what is the value of phi n plus 1. This is not defined at all. So these two points, x1 or xn, Laplace equation cannot be applied. Then how can we proceed? Of course, boundary condition can be a remedy on this situation. Boundary conditions like phi 1 becomes 0 can be transformed in this way. 1, 0, 0 and all 0 multiplied by phi 1, phi 2 up to phi n. This row vector and column vector multiplication just gives you phi 1 only, because all other entries are identically 0. So whatever values phi 2 has, that doesn't matter. The value of phi n does not contribute to this multiplication. It gives you just phi 1, and that is just 0. We can repeat it once again for xn, then it gives you 0 and 0 up to n minus 1th entry, and the final one is 1. That is given by phi 1, phi 2, and phi n minus 1 and phi n. When we evaluate this multiplication, the first n minus 1th components doesn't matter, and only the final one gives you phi n. Then that is given by 1. So now from the boundary condition, we can easily find out two more conditions, and they can be placed in the first row and nth row of our system. Then how does it look like? Our system will look like this. Here we have the vector, and here we have right hand side, and here we have a square matrix, and it is from its second row to n minus row, from 2 to n minus 1, since we are working with Laplace equation, we have all 0. And the first one, we have 0, but this is related with phi zero component. And here we have number 1. It is because we have assigned phi a equal to 1. That will be the right hand side of our system. And also there is a square matrix, and it's 2 to n minus 1 row. There is a stamp like 1 minus 2 1, 1 minus 2 1. This stamp is just shifted and made until we arrive at the final row n minus 1 row. And the first row and the final row, the first row and the final row, we have just a diagonal component 1. 1 comma 1 component becomes 1, and n comma n component becomes 1 because they are corresponding to the boundary condition. This is an 5 example. Since we have discussed about the general number, so I guess that this is all good enough. Then let's go to the actual MATLAB example. So I will just skip it. But if you are curious about the real demonstration, then please watch our L2.5. In that lecture, recorded lecture, I just show you the live demonstration about this example. You can do it. And we have one important concept to be discussed. So here we have the notation, the Poisson equation. Why do we call it as Poisson equation? Poisson equation and Laplace equations are compared in this part. Both of Laplace equation and Poisson equation is not directly related to our problem. They are just mathematical form for differential equation. If we have Laplace operator exerted on our solution vector, when that gives 0 everywhere, that is called Laplacian. And when it gives you certain source function, that is called Poisson equation. This is the meaning of Poisson equation and Laplace equation, not directly related with physical problem of our interest. But quite frequently, I will say Poisson equation, and Poisson equation. So you have to keep in mind why I call it as Poisson equation, although it is not strictly the Poisson equation. I mean that when I say, in summary, when I say Poisson equation, then actually it means Gauss law. Oh, Gauss law itself can be casted into Poisson equation in following conditions. Okay, if we consider the material responses, then the general form looks like this. This is the general form of Gauss law within a dielectric material. So in order to make it in a form of Poisson equation, we have to have certain approximations. Okay, the first one, this displacement vector should be interpreted as this form. Okay, this relation, when epsilon permittivity is scalar, then we can write down in this form. Of course, generally, between displacement vector and electric vector, we need a tensor permittivity. However, in this course, we will neglect this tensor permittivity. The permittivity is always regarded as a scalar one. So this is one first approximation. The first approximation, and after that, one further step is electrostatic approximation. When electrostatic approximation is applied, the electric field can be just related with the electrostatic potential. Of course, in general, we have to consider time derivative of a magnetic field, but in the electrostatic approximation, that term is neglected. Okay, and finally, this is already approximated, not approximated, but valid at certain cases. And finally, when we have a constant position independent epsilon, then we can finally have Laplacian operator exerted on phi becomes rho over minus rho over epsilon. Then this form is really the Poisson equation. So historically, people at the beginning of the computational microelectronics, they solved this equation because, at the time the material was just they considered only a single material. So no problem about calling it as a Poisson equation. But later, they have introduced silicon and silicon dioxide or other different dielectric materials. Then we cannot make the final simplification. This is not allowed in our case, in our general case. Then actually we have to solve this form. This form is not in the form of a Poisson equation, but due to such a historical reason, we still call it as Poisson equation. So therefore, I will just take this convention because all other guys in this field call it as Poisson equation. So I will call it as Poisson equation. But please keep in mind that in rigorous sense in mathematics, this is not the Poisson equation. Sometimes people call it as a generalized Poisson equation because here we have position dependent coefficient in front of gradient operator. Let me wrap up today's lecture. You have already the third homework, and third homework has two problems. The first problem is just a repetition of our example with different boundary conditions. You can do it quite easily. And second question is a little bit more difficult. This is not the Laplace equation, but I'm asking you to solve Poisson equation. So here we have Dirac delta function located at x equal to half a. So please think about how can you treat this Poisson equation, and I expect your quite smart answers. Please keep in mind that the due is next Monday, and if you have any question, please send me an email. Then I can try to answer um, your question. Okay, thank you and see you next Monday. Bye.